ask me.
Hello, ma'am.
Yeah, Shmushta.
Ma'am, can you discuss about the consistency?
About which part?
Ma'am, lecture 8.9,
Okay,
properties of estimation.
consistency. Okay.
Hmm.
So this part, see, this part will not be asked anywhere in the exam. Consistency should, it's not needed for the part.
But ma'am, for final exam,
No, it will not be there. Consistency will not be there.
okay, ma'am.
So it's mostly mathematical part. So we see the weak law of large number, and
Hmm.
we check whether the estimator is consistent or not, and we say the convergence in probability and all that. So all that you do not know for now. It's more to math side. So you can just leave it for now. It's not needed.
Okay, ma'am.
Yeah.
And ma'am, from week 8, what are the important topics for our quiz?
Important topics for the quiz. So what all we have covered. So we started with the error, then we went to estimators. Then you should know how to check bias and biasness. You should know how to check mean square error. You should know how to estimate the parameter, your unknown parameter using method of moments and the maximum likelihood estimator. So these two you should know very properly how to estimate using method of moments and how should you estimate using maximum likelihood. And then, yeah, till here, I think after that, nothing is there.
Okay, ma'am.
So you should know how to check biasness. You should know how to calculate mean square error. You should know how to estimate your parameter using method of moments and maximum likelihood.
Okay, ma'am.
So all of you have done week 8, finished week 8.
Yes, ma'am. Just finished watching the lecture videos
Okay,
today.
okay. So any doubt in the lectures?
No, ma'am. If I have, I will tell you.
Yeah. So did you find the week 8 more difficult or easy than week 7?
We have to give some more time in this week,
Yeah.
I think.
Anybody has any doubt from lecture, any doubt from the questions?
Yeah, I was unable to solve this week 8.4 activity question. One and
8.4
all.
activity questions. Okay, I will check the questions. Which questions you want me to solve?
At question 1,
Question 1. Okay. Okay, so you have NIID samples from a distribution with unknown mean mu and standard deviation 2. One of the estimator is x1 and you have to find the bias of mu hat. This question only, right?
yes.
Yeah, I will share the screen. So you have x1 up to xn, all are IITx. There is a mean given to this. Mean of the distribution is mu and variance is sigma square, right? And you have
Yes.
an estimator mu hat that is given to be x1. That is the first observation. Now you have to
Sigma
check.
is not.
Sigma
Sigma is 2.
sigma is 2. Okay. So you have to find bias of mu hat.
Yeah.
Sorry, bias of mu. Bias of the estimator.
Bias of mu hat.
Yeah, mu hat. Okay. Yeah. So bias of mu hat you have to find. So what is bias? Bias is expectation of mu hat minus expectation of mu, right?
Yes.
So expectation of mu hat, what is mu hat? Mu hat is x1 and expectation of mu will be mu. And each of these xi's are IIT x. So, and we know that x has the distribution with mean mu and variance sigma square is 4. So what is expectation of x1? What should be the expectation of x1?
Not sure of that.
Okay, see, what do you understand by x1, x2, xn, IIDx?
These are samples from the distribution.
Yeah, so these are the samples from the distribution x. So the the distribution for each of the xi's will also be same as x. Right? And if for expectation of x, if expectation of x is given to be mu, it means expectation of each of the xi's are also mu.
Okay.
So there you have to just, so expectation of x1 will be mu and this is mu, so that is 0.
And where does this thing of dividing by n come in? Is it for variance or
Where is dividing by n?
like if variance of the whole set of samples is known?
Okay. So you have x1, x2, xn, IIDx, right? Now, if I am writing, let's say we have an estimator, you know, x bar is an estimator. So an estimator for mean of this sample. So this is sample mean is x1 plus up to xn divided by n. We know that expectation of x bar is same as mu. If x has the distribution mean mu, variance sigma square. Expectation, it is given to us that expectation of x is mu and variance of x is sigma square. Okay, so expectation of x bar, do you know how to calculate expectation of x bar? Okay, I will explain that. Wait, I'll explain somewhere. Yeah. See, you have x1 up to xn IID x. Now you have taken, these are the sample of taken from x and those are IID. It is given to us that expectation of x is mu and variance of x is sigma square. Now I'm taking the sample mean. Sample mean, we know it's an estimator for mean. So x bar is equal to x1 plus up to xn divided by n. Now if we find the expectation of x bar, so it is going to be expectation of x1 plus up to xn divided by n. So this n here is a constant, so we can pull
Take
it
it
out.
out.
Yeah. So 1 by n expectation of x1 up to xn. And we know that expectation follows the linearity property. So you can write 1 by n expectation of x1 plus up to expectation of xn.
Xn. Yeah.
And each of these expectation of xi is what?
That is mu.
Right? So you will sum it for n times. So
N mu. So
n,
it's equal to mu.
yeah. So it will cancel out and will be mu. So that is why we say that x bar is an unbiased, x bar is an unbiased estimator of mu. Okay, because expectation of x bar is mu. So if you find the bias of x bar, it will be expectation of x bar minus expectation of mu. So that will be 0. So that is why x bar is an unbiased estimator of mu. So this is how we find it. Now let's see how do we find variance of x bar. So variance of x bar is variance of x1 plus up to xn divided by n. So this n is a constant, so we can pull it out. So it will become 1 by n square, right?
Yes.
And variance of x1 plus up to xn. Now each of these x are IIT independent, so we can write it as
Variance of x1 plus variance of x2.
variance of xn. So what is variance of x1?
Sigma square.
Sigma
So
square.
it will become n sigma square. So
N sigma square.
total is sigma square by n.
Sigma square by n. So what you say, this sigma square by n, this is the variance for sample mean.
Okay. And this variance becomes almost 0 as n increases.
As n increases, yeah, it becomes, yeah, it goes to 0. Sorry. Yeah. Any other doubt?
I just started solving it, so I was stuck at that question.
Okay, okay.
In 8.3 also I had a doubt in the second question, but the solution was available on Discourse.
Yeah, today only I put.
Hello, ma'am.
Yes, yes, Mr.
Ma'am, any formula sheet will be given like will 1 to 3?
Week 1 to 3.
Hmm.
For week 4, 5, 6, it is provided, right? It's there on the portal.
Yeah, it's uploaded.
Yeah, for week
Oh,
5, 6, it is there. We will provide for week 7, 8, 9 also.
okay, ma'am. I will check it now.
Yeah, 4, 5, 6, it's there. You can check it.
Okay, ma'am.
And the distribution sheet that was being used by Professor Andrew during the solve with us, that will be provided like that itself during the exam.
During the exam, we will let you know if it will be there. Like
Okay.
if like for some distributions like gamma, beta, chi-square, and all the Cauchy, for all that, don't need to remember all that. So whenever it is needed, it will be there in the problem.
Okay.
Anybody has any more doubts? Purnima or Subhiti, you have any doubt? Bimlesh?
No, ma'am, yet to watch all the lectures.
Okay. Nobody has any doubt?
The graded assignment for week 7, the solutions will be uploaded, or
Yeah, sorry for that. We'll upload it by Monday. Yeah. Monday or by tomorrow, we'll upload the solution.
Ma'am, if you can explain the maximum likelihood estimator.
Maximum
That is-
likelihood estimator.
Yes, ma'am.
Okay. that. See, so you have, let's say you have a parameter theta, and you want to estimate this parameter. This parameter you know is unknown, some unknown constant. Now you want to estimate this parameter using maximum likelihood. Uh, so you can write this estimator. Let's say it is theta hat ml. So what we do is the first step. So okay, let's first see for Bernoulli. To take one example. Let's say X is Bernoulli P, where we know where P is unknown, where P is unknown. Now we want to estimate this parameter P. So what do we do first? We first write the PDF or PMF of the function. So what is the PDF of this function? It will be uh, P to the power, let's say, okay, first we'll write, let's say x1 to xn are IID samples from X, that is Bernoulli P. Now we want to write the PDF for this function. So if let's say there is only one, so it is 1 minus P. Okay, I'll just write the step. First step, you write likelihood function. Likelihood function. Second step, you should do argument of max of product of effects I, theta 1, theta 2, to theta n. Oh, it's not actually wrong. So max of, so this is I varying from 1 to n, which is for the samples I 1 to n. And you want the argument where all this data will be, this will go to, so on. Yeah, all this this likelihood function is maximum. You want that point. So how do we write the likelihood function? So this part inside the bracket is known as likelihood function. Likelihood function. So for Bernoulli for Bernoulli distribution, this likelihood function is going to be uh, p times p to the power w 1 minus p to the power n minus w, where all these xi's are samples and w is number of time success occurred, and n minus w is number of times of failure, right? So this is going to be the likelihood function. Let's say we denote this function by hp because it is a function of p. So let's say hp is p to the power w 1 minus p to the power n minus w. Now to maximize this function, we want to maximize this function. So what we do is instead of maximizing h of p, we'll maximize log of h of p. So if you take the log both sides, so it will be p to the power w 1 minus p to the power n minus w. So if you take the log, it will become w log p plus n minus w log 1 minus p. Now,
Excuse me, ma'am.
yeah.
Ma'am, all time we have to take log.
Yeah, because
Is it
it's
necessary?
easier. It's easier to differentiate if you take log, because the terms will split out, because you have the PDF in product form, and if you take the log, it will be in, it will separate out using the summation sign and all that. So it's
But ma'am,
easier.
if
It's
our
always
function
easier.
is easy, then
Yeah, this is easy, but if you see complicated functions like normal distribution, gamma distribution, Poisson, all that becomes difficult. So we generally like use take log and maximize that function, that log likelihood function.
hmm,
Yeah. So
okay, ma'am.
now if we differentiate this part, so this will be what? differentiate with respect to p. So let's say this is g of p. You want to differentiate with respect to p. So it will be w by p plus n minus w 1 minus p. And since it is a minus sign, so this will become this. So w by p minus n minus w by 1 minus p. Now what? How do you solve this? So you'll have to equate this to 0. So this will become w by p equals n minus p upon 1 minus p. So that is w1 minus p equals p n minus w. So again this will be w minus pw equals p n minus pw will cancel out, and you will get p equals w by n. P equals w by n. So your estimator p hat ml will become w by n, and this is nothing but x1 plus up to xn divided by n. So this will become your ml estimator. This is maximum likelihood estimator.
Ma'am, why is W is equal to x1 plus
Why w is x1
x2?
plus x2 up to xn? Yeah. So see, each of these xi's are Bernoulli p. So if you take all those samples, so if you write x1 plus up to xn, so what does it model? It models binomial, right? Binomial distribution. And what does it shows? Binomial number of successes, correct?
Right.
Number of successes in n trials. So this is number of successes. And what was w? We have taken w to be number of successes.
Right.
Yeah, so that is why it is x1 plus x2 plus xn divided by n.
Okay, so here n is number of success,
Yeah,
that up to n means number of successes. X means
your voice is
if
break.
there is three successes.
Your
Hello,
voice is
ma'am.
breaking. Can you repeat? Your voice was breaking.
If said that there is three successes, here n would be 3.
Yeah. If you are saying 3 successes, hello. So this is number of successes in n samples. Hello. Am I audible?
Sorry, ma'am, I got
Yes, you are.
disconnected.
Yeah. So this is number of successes in n samples. So let's say if I say you're tossing a coin. So for each of the trial, it is either head or tail. So if I define my success to get a head, so this probability will represent by p. This is our success. So success, let's say each of these xi you're representing by 1 if it is success, or 0 if it is a failure. So if you write x1 plus up to xn, so this will give you number of successes, right? Number of successes in n trials, in n samples, right? This will give you number of successes in n trials, because let's say in the first trial, you got a success, so you mark 1. Okay, let's write it here. So x1, x2, x3, x4, x5. Suppose you have 5 samples. Now in the first sample, I have observed a success, so I will give 1. Second, I have observed failure, so I will give 0. Third, I have observed success, so first, 1. So again, fourth, we have observed success, so 1. And there also, let's say we have observed failure, so it's put mark 0. So if I write x1 plus x2 up to x5, what does it show? It shows number of successes in all these 5 samples, number of successes, and how many of them? They are 3. So if I, yeah,
Understood.
understood? Okay. So one more example, we'll see.
Thank you.
Yeah. Do you want me to two more examples?
Yes,
I
yes,
think
ma'am.
professor
Please.
had mentioned that when you put this x is equal to 1 or 0, you call it as a indicator random variable.
Yeah. Yeah. Indicate the random variable. Yes. Do you want me to do more problems or just fine?
Now do it for the normal.
Normal distribution.
Yes, ma'am.
Okay. Okay.
Excuse me, ma'am.
Yeah. Yeah, Samstha.
Ma'am, we know that there are some points named saddle points where
Saddle
we
point.
where the derivative is 0, but the second derivative will not give any possible value. That is not a maximum point or minimum point.
Yes.
So in that case, it will not. We will not get the maximum likelihood, right? So that is a
Uh,
gap.
yeah, there, like, yeah, if some point is a saddle point, we'll not get the maximum or minimum. But
But we are
it's not,
claiming its maximum likelihood.
yeah, but that point is not a saddle point. Are you from the maths background?
Yes, ma'am.
Yeah, so you can try to check all those we have done in lectures. None of the
It's
points,
also in our maths too.
it's also in your maths too. Okay, okay.
Yes, ma'am. Saddle points.
So you can try to check for the estimators, all those estimators, whether for those points it is a saddle point or not.
Hmm.
Okay, so we'll do for normal. So let's say x is normal mu sigma square. You are taking some samples x1 to xn. These are IIT x. Now we have to write first the likelihood function. So likelihood function will be product of I varying from 1 to n. This is 1 upon under root 2 pi sigma e to the power minus 1 upon 2 x I minus mu 1 sigma whole square. So yeah, this is going to be so you have two estimators here. One is mu and another is sigma square. Two parameters, sorry, mu and sigma square, and we want to estimate both those parameters. So let's say first we are trying to estimate mu. First, we are trying to estimate mu. So if we want to estimate mu, so what we will do is we will whenever we have to differentiate, we will differentiate with respect to mu, keeping sigma constant. So first, if we write likelihood function, so this whenever there is a constant term, you can neglect that term, because if we do the differentiation part, this will be like that part will be neglected. So you can remove this constant part, just ignore that part. So you will be left with 1 upon sigma to the power n from there, because sigma you have to multiply n times, 1 by sigma to the power n. This will be e to the power minus 1 upon 2 sigma square. And this will become xi minus mu whole square, I varying from 1 to n. This step is clear.
Yes, ma'am.
Now you take the log.
Could you please repeat once?
Yeah, so see, you have to multiply this, right, n times for each of these xi's. So this will become, so we can ignore the constant term. So 1 upon under root 2 pi is a constant. We can ignore that, because when you proceed further, like whenever you have to differentiate, taking log, that part will get cancelled out. So you don't have to worry about taking the constant. So whenever there's a constant, just ignore that constant. Now, if you write this, if you expand this, so you will get 1 upon, ignoring the 1 upon under root 2 pi term, you'll get 1 upon sigma e to the power minus 1 upon 2 sigma square x1 minus mu whole square. Then you will get again 1 upon sigma e to the power minus 1 upon 2 sigma square x2 minus mu to the power whole square. This will go on till n terms. So this is again e to the power minus 1 upon 2 sigma square xn minus mu whole square. So this is n times. So this will become 1 upon sigma to the power n. Now taking the exponential part, we get the exponential part. So this will become minus this minus 1 upon 2 sigma square. You can take as a common term, and all these xi minus mu whole square will get added. So this will, you can write xi minus mu whole square, so this whole square I varying from 1 to n. Is this okay?
Yes.
Yeah. Now you have to take the log. So log of L. So consider this and this as two terms. So if you take the log, so first will be log of 1 by sigma to the power n plus log of this term, log of this term. So you know that log of e something will
It's
become this
power itself.
as power itself, right? So the next term I can write n log of 1 upon sigma minus 1 upon 2 sigma square sum over xi minus mu whole square I varying from 1 to n. So again log 1 is 0, so this will become n log minus of log sigma, right? This will become minus of log sigma minus 1 upon 2 sigma square uh, sum over xi minus mu whole square I varying from 1 to n. So now you have to maximize this function. So maximizing this function, okay, let's split this part also inside the bracket. What's this? So this is minus this, so minus 1 upon 2 sigma square. This will become xi square sum over xi square plus mu square minus 2 mu xi. So you want to maximize, you want to and you want to estimate the parameter mu. So whenever you have to differentiate, you can ignore, you can treat sigma as a constant. So if you treat sigma as a constant, this derivative will become 0. So just neglect that. Now you are left with only this part. So if you differentiate, you will get uh, minus 1 upon 2 sigma square, you can treat constant. This will be sum over xi square plus 2 times mu minus 2 xi, and you have to take this to 0. Uh, there is a minus sign right here. Minus sign.
Hello, ma'am.
Yeah.
Ma'am, xi square are not constant.
Xi squares are constant. Yes, xi squares
Then
are constant.
the,
Yeah.
shouldn't be the
Wait.
differentiation be
See, so we want to maximize this function minus of 1 upon 2 sigma square. So this part we want to maximize. So this is minus sign here. So if we want to maximize, it means it is same as minimizing 1 upon 2 sigma square sum over xi square plus mu square minus 2 mu xi. This is same as minimizing this function. So if you minimize this function, you take the derivative, you will get 1 upon 2 sigma square. Can I try to expand this? This will be 0, and this will become n mu square minus 2n mu plus xi, right? X2 mu xi, so this will come xi x1 plus 2xn. Yeah, so this will become minus 2 mu. Can write this as n x bar. Yes, we can write this n x bar. So if you differentiate this now, you will, oh, yeah. So if you differentiate it now, you will get 1 upon 2 sigma square 2n mu minus 2n x bar. Equate it to 0, you will get n mu equals nx bar. So mu equals x bar. X bar you know is x1 plus x2 plus up to xn by n. So your ML estimator for mu is x1 plus up to xn divided by n. This is our ML estimator for mu.
Only because there is negative sign, we are
Yeah.
saying the argument of minimum.
Yeah, because we wanted, if we want, like, what is maximum likelihood thing? So you want to maximize the likelihood function. In this case, your likelihood function is minus of this term, right? Minus of 1 upon 2 sigma square sum over xi square, this term. So if you want to maximize some negative quantity, so it is same as minimizing this positive quantity, this term, right?
Yes, that is ultimately
That is
becoming.
why, yeah, that is why maximizing this we can write as minimizing 1 upon 2 sigma square, this part.
Okay, ma'am, understood.
Ma'am,
Yeah.
can you explain the minimizing part once again?
See, you want to maximize this negative, this term, right? You want to maximize this term. So if you want to maximize something, and if you want to maximize minus of something, so if you remove this negative term, it is same as you want to minimize this, let's say uh, you have minus of a, let's say this is a, so you want to maximize this term. So if you want to maximize this term, will be same as you want to minimize a, because the less a is, this is a real line. So you know that minus 2 is greater than minus 3, right?
Yes, ma'am.
Yeah. So if you want to maximize, if I want to maximize my minus a, so a you don't know what it is. So if you want to maximize your minus a, it means you want to minimize this. So it means the lesser the value of a, the maximum minus a will be. Same as here. So see, minus 2 is greater than minus 3. You wanted to maximize minus a. So if you want to maximize a, so you will take the minimum of a. So we will take a to be 2, right?
Yes, ma'am.
Right? Because minus 2 will be greater than minus 3. So that is why I'm saying that if you want to maximize this, you'll have to minimize this a.
Yes, ma'am. Got it, that part. Ma'am, once again, please explain the steps.
Yeah, it becomes a little messy here. Yeah. So see, I wanted to maximize my likelihood function, and we wanted to estimate the parameter mu. So I can treat sigma as a constant. So if you treat sigma as a constant, if you take the derivative, it will cancel out. So what it will just take, you'll just take, now you want to just minimize this part. Okay. So if you want to minimize this part, I will write it here again. So minimize 1 upon 2 sigma square sum over xi square plus mu square minus 2 to x bar xi. So just expand this. So you will get x1 square plus x2 square up to xn square, right? Then n mu square, correct? And this will
Yes.
be 2 mu. I'm saying sum of xi. So what is sum of xi? This is minus 2 mu x1 plus up to xn. And what I have written is, so we know that x bar is x1 plus up to xn divided by n. So we can write x1 plus xn as n x bar also, right?
Yes, ma'am. Yes.
So you can write this as minus 2n 2n mu x bar, this term as minus 2n mu x bar, correct? Now you want to minimize this. You want to minimize 1 upon 2 sigma square sum over xi square plus n mu square minus 2 n x bar mu. You want to differentiate it using with respect to mu. So with respect to mu, if you differentiate, so you'll have to treat sigma as a constant. So sigma you treat as a constant. So this will be 0, and this will become 2n mu, and this will be minus 2n x bar. Now after differentiating, you equate it to 0. So if you equate it to 0, you will get 2n mu equal 2n x bar. This will cancel out and you'll have mu equals x bar. Is it okay?
Yes, ma'am. Got it.
Yeah. Same you will have to do for sigma square. So if you have to do sigma square, you will differentiate you with respect to sigma there. You can write, yeah,
One small conceptual question, just want to clarify one concept.
yeah.
Please refer 8.6 activity question number 2.
Wait, let me check. Which question?
That is one axis uniform
Activity
distribution.
activity 8.6.
Activity 8.6 question number 2.
Question number 2, right?
Yes.
Yeah. So you have x to be uniform 1, 2, 3 up to n. N is unknown. Consider sampling 1, 5, 4, 8, 11, 9, 15, 17, 16. Okay. From the distribution x, find the maximum likelihood estimate of n. Yeah. So what you'll have to do is, so how did you proceed?
Actually, sir said in one of the lecture uh, that when the distribution is in uniform, and if you want to estimate its most likelihood value, it should be the maximum of the sample observed. That means if I observe x1 to xn sample and I want to see the maximum likelihood in this distribution, it will simply the maximum value from x1 to xn that I observe. So if I apply that, then the same thing it's coming 20. But I do not understand the rationale behind this.
Okay. If you'll apply, you will get what? 20, right? Not 10. 20.
Because the sample size is given 1, 5 like this. So out of
Here,
that
how many
20,
are there? 1, 2, 3, 4, 5, 6, 7,
13, I think.
13, no?
Hmm.
Uh-huh. So Yeah. So what you do?
So out of this 13 sample, the maximum one is 20 that I still, that I realize, rather I say.
Hmm.
So 20 will be the maximum likelihood for in case of n.
Yeah. You want to know why?
Yes, yes, yes.
Okay. So see. So this you want to know about this question or in general?
You can discuss with this question, then I will
Yeah.
understand the general theory.
Yeah. Yeah. Okay. So this is discrete uniform. So some samples is going till n, and you know that the PMF of x is 1 upon n. Correct.
Right.
Now, some samples are given to you. I don't remember what exactly it is. Some samples you have.
You
Okay.
take any sample.
Okay.
Say
Let's
10
say
sample you
I'm taking
realize.
1, 2,
Yeah,
4,
yeah, yeah.
9,
1, 2, 4,
1,
15, 7, 8, like that.
3,
10 sample.
11, 12, 1. Okay. So these are my 10 samples I have taken.
Mhm.
So I want to maximize if okay. So if I want to, yeah. So the PDF is 1 upon n. So PDF is given to be 1 upon n. So you want to maximize your 1 upon n. So if you want to maximize your 1 upon n, it is, and you know that n is in denominator. So it is same as you want to minimize your n.
Minimize my n, right?
Yeah, you want to minimize your n, and yeah, and so each of these samples are here. So 1, 2, 3, 4, 2, and each of the samples are there. Okay. There. This is your n. This is your n. Uh, So you want to minimize your n. So each of these samples that you take will be in this, will be either 1, 2, 3. It will be in some discrete point, right?
Yes.
So if you take why we are taking minimum is, let's take 11. If you take 11, what will happen is it will go only till 1, 2, 3, 4 up to 11. So if I take 11, it will stay only till 11. So your sampling has the point 12, but if you have taken 11, you cannot you're ignoring, where will you put this 12? You need this 12 to be also there, right? Because 12 is the maximum here. This is a general discrete case I'm talking about. If I'm taking 11, let's say I'm taking n to be 11. So if you take n to be 11, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But your sample has term 12 also. So this is not possible. So that is why you have to take the maximum of the whatever is occurring in the sample. This is in general discrete case. Now let's say you have, sorry,
No,
you have,
ma'am, just
yeah.
just
Like,
clarify
yeah,
something.
yeah, yeah.
You said ki suppose this 1, 2, 4, 9, 2, 10, 11, 12, some sample size, some sample I realize from a distribution of x, where
Yeah,
x is uniformly distributed between
or
1 to
1
n.
to n. Yeah,
Okay.
those are discrete
Now,
points.
Yes. Now I want to calculate the n. That means how far this uniform distribution it's spread, so that I can realize the maximum likelihood, right?
Yeah, yeah.
This maximum likelihood means is the probability of occurrence, right?
Point where your likelihood function will be maximum.
That means it generally tends towards the expectation of x or expectation of that distribution, the first moment
Generally, yeah,
generally tends. That means since the each point probability is 1 by n
yeah.
here,
Hmm.
I want to maximize this 1 by n into this distribution. But
Hmm.
you said ki if you take 11
Hmm. If you take n to be 11, yeah,
n to be 11, then the 12th part is we are omitting.
yeah,
That is why it has to be
12.
12. And suppose this this sample is still 1 to n, then then n is n, because that is the maximum value.
Huh.
You are saying this.
Now let's look for the continuous uniform distribution. So
Okay.
let's say your x is uniform 0 to a. Okay. Now you have taken some samples x1, x2 up to xn. They are in IID x. So this is your, let's say 0. This is your a. Each of these samples are here. Now we want to, what is the PDF? PDF is 1 upon b minus a, that is 1 upon a. So this is the likelihood function now, 1 upon a to the power n, and we want to maximize this. So if you want to maximize this, it means you'll have to minimize a, correct? You'll have to minimize a,
Right.
minimize a to the power n. So, and you know that each of these xi's, x1, x2 up to xn are less than equal to a,
Yes.
right? So what is the minimum value a can take?
A can take 0.
Minimum value a can take. So whatever the maximum you will get from this sample, that is the least a can take, right?
Oh, A is now distribution endpoint. Okay. Yes.
Yeah,
Yes.
yeah, this
Yes.
is a, yeah. So whatever maximum these samples will take, a will for that max of x size, this a will be minimum.
For max of
For
xi, A will be
max
minimum.
of
Right.
x1 to xn, a will be minimum.
Right.
So in this case, your estimator for a is max of x1 to xn.
Okay. Clear. Clear, ma'am. Clear.
Yeah. Okay. Anybody else has any doubt? Anybody has any doubt?
If do not have other people do not have doubt, then will you please discuss this uniform distribution discrete and continuous part, the estimator means maximum likelihood estimator.
I just discussed, no?
Sorry, not uniform. This geometric,
Geometric distribution, okay.
only discrete part. And also the confidence interval.
Confidence interval, okay. So geometric distribution has a did in the class?
No.
Okay. So you have x to b geometric b. You are taking some samples x1 to xn. IIT x. Now you want to estimate b. So do you want to know method of moment also, or just likelihood?
You derive from both sides, that will be fine.
Okay. So we know that expectation of x is what? Expectation of, sorry,
Expectation is, sorry, 1 by
1 by p, right? Yeah. Now this is your m1. So your p will be 1 upon m1. So this will be n upon x1 up to xn. So you got the estimator using method of moment as n upon x1 up to xn.
yeah.
Now
From ML side.
from ml, what it will be? So your likelihood function will be product of 1 minus p to the power k minus 1 into k, and so the product will be 1 minus p somebody has raised hand. Yeah, tell me.
But ma'am, I approach this problem in a different way.
Which problem?
This email, finding the email through geometric.
Can you tell me how did you
So
approach?
this k for this geometric distribution, the PMF 1 minus p k minus 1 into p. First of all, that is p, not k.
Sorry. Where?
This 1
Oh,
minus,
okay. Yeah.
that is p, and this is for a particular value when x equal to k.
Yeah, this is for x equals k. Yeah, correct.
So for this, I substituting this k is equal to x1, x2, x3, and that multiply till up to n. But somewhere I'm not getting the answer. That is why I am asking this.
What you did? Can you just?
The first step I write in 1 minus p, x1 minus 1 into p. You write it.
Wait, I will just write it somewhere. One minus p
1 minus p to the power x minus 1.
minus one
x1
p.
minus 1. Sorry, first
Yeah.
point is x1 minus 1 into p.
Yeah.
Please write
That
it
is
on the
correct.
whiteboard.
Okay. Yeah, wait. See,
Yeah, 1 minus p.
yeah, so likelihood function will be product of 1 minus p to the power xi.
Xi minus 1 into p.
I right from 1 to 1. You did this, right?
Yes, yes, I did this way.
That's right. So this is 1 minus p to the power x1 minus 1 p into 1 minus p x2 minus 1 p up to 1 minus p xn minus 1 p.
Correct.
So you will get p to the power n 1 minus p to the power
One.
sum over xi minus 1 I varying from 1 to n.
Correct.
Now you will take log. Chat box. Okay. So now you will take log. So if you take the log, you will get n log p plus sum over xi minus 1. I is varying from 1 to n. Log of 1 minus.
But
Wait.
This xi minus, this can be sigma xi minus n.
Yeah, sigma xi minus n. I will write it as pn 1 minus p x1 plus up to xn minus n, correct?
correct.
Now you take the log, you will get x1 plus up to xn minus n log 1 minus p.
But I didn't take the log and solve that. But somehow
Oh,
the
okay.
answer is not matching. I don't know.
What
Anyway,
did you get? So if you now you differentiate this, so you'll get n upon
differentiate this
p
with
plus
fxgx
xn up to
formula.
xn
Yes.
minus n upon so you get minus here 1 minus p. We'll have to make it 0, so it will be again n minus np equals p x1 up to xn minus np will cancel out and you will get p to be n upon x1 plus up to xn.
Yes, it's supposed to be, but I didn't take the log and simply differentiate with fxgx formula, and I didn't get this at last. I get n minus np is equal to p into x plus dot dot xn plus np. So I am not able to cancel this np term. It is within my equation, and that is why I am not getting the answer.
You try it with log, this should be correct.
Okay.
So in this case, both using MME and ML, we are getting the same estimator.
Same estimate. Ma'am, please discuss the confidence interval
Confidence interval, yeah.
in general.
Yeah.
Excuse me, ma'am.
Yeah.
Ma'am, is this an open session?
Yeah, this is an open session.
So I have a question to ask. Can I ask it now, or will you explain confidence interval first?
Okay, you can ask the question.
Yeah, ma'am, it's regarding one of the things that you said in a previous solve with instructor session. I have sent you the link to that. Can you kindly open the link so we'll have the same thing in front of us? Like,
Okay. Can you tell me which part?
ma'am, it's I sent you the link with the timestamp itself, ma'am. It's 38 minutes 57 seconds.
You have sent me the link.
Yeah, in the chat box. The last solve with instructor session that was taken.
Right.
You contacted it yourself, ma'am.
Okay. You are Prithudeep.
Yes, ma'am.
Okay. Yeah, tell me which.
Yeah, ma'am. There are like first you have written xi belongs to normal distribution of 0, 2, and after that, ma'am, do you have the question open in front of you, right?
Yeah. I have it.
Okay, and then you wrote xi square is like gamma distributed with
Gamma 1 by 2.
yeah, and
1
1 by 2.2.
Yeah.
So you calculated the
Not 2.2. It is 2 into 2.
okay, yeah, I'm sorry, ma'am, 2 into 2.
Huh.
So you calculated the corresponding expectation and variance,
Huh.
but after that you wrote x1 square plus x2 square dot x100 square is
Will follow
distributed.
gamma 100
Yeah.
by 2. Yeah.
So like, can you explain the difference between that second line and third line there? 100 by 2 and then 1 by 2.
100 by 2 and 1 by. Where is 1 by 2?
Sorry, 1 by 4. I'm sorry, ma'am. 100 by 2 and 1 by 4.
Yeah, so x1 square plus up to x100 square, like each of these xi square are, we know, gamma 1 by 2, 1 by 2, that is 1 by 4. So if you sum the gamma distribution, let's say your x is, I will just write it. Mhm. Just write it. So each of these xi square were gamma 1 upon 2, 1 upon 4. Now,
Yes, ma'am.
if we write x1 square up to x100 square, each of this will become gamma n upon 1 by 2, n means n alpha into 1 by 4. So you must have seen the property in the lecture that sir
Yes, ma'am.
has given, that
Yeah.
if x is gamma alpha beta and you have taken n samples from x, so x1 plus up to xn will follow gamma n alpha comma beta, correct? So
Yes,
this
ma'am.
is what this thing is. So there I think n must be something 100 or 1000.
Yes, ma'am. It was 100.
100.
Then my confusion arose actually when I was trying to take the mean, that is the expectation and variance myself. Instead of using gamma half and 1 by 4, I did it with gamma 100 by 2 and 1 by 4. Can you explain me where I went wrong, ma'am? Why did you take expectation and variance from the first one instead of the second one?
Okay, so we had to find probability x1 square plus up to x100 square. Just a question. Um, can you tell me what was that?
Ma'am, to find probability of x1 square plus x2 square dot till x 100 square greater than
Greater than
220.
greater than 220. Now we know that each of these xi square are gamma. So let's say I'm writing x1 square as y1, x2 square as y2, xn square as yn.
Okay.
So each of these sum, so it is same as x1, x2 up to xn. So whenever you write the CLT form, so what is that? So it is y minus n nu upon sigma under root n is normal 0, 1. Uh,
Yes, ma'am.
So in this case, what is your y? Y will be x1 square plus up to x100 square, right?
Yes, ma'am.
If I take this. Now what is n? N is 100.
Yes, ma'am.
X1 square to x100 square, n is 100. And what is mu?
Yeah, ma'am, here is the confusion. We take mu with gamma 100 by 2 and 1/4 or
No.
mu with gamma half
Gamma.
and
So let's
1/4.
say if you had the sample x1 up to xn and they are from IITx, and the expectation of x was mu and variance of x was sigma square. So if you write y minus n mu upon sigma under root n, so this mu is the expectation of x. This mu is the expectation of x.
Okay.
Yeah, so in this case, your mu is what? Mu will be expectation of xi square.
Ma'am, just to clarify, that property
See,
of
yeah,
no,
it's the
ma'am, go
same thing
ahead.
only. It's the same thing. So you have y to be this, right? If you find the expectation of this, you will get the expectation of y1 plus up to expectation of yn. So it will be nothing but n times expectation of y. So expectation of each of these y's are what? They are gamma 1 by 2, 1 by 4. So 100, yeah, so that expectation is n is 100 and that is alpha by beta, right? So alpha
And
is what?
220 minus 50.
Uh, Sorry?
It will be 220 minus 50. Now, ma'am, we will subtracting mu n from 220.
Oh, no. I'm not going to that part. I'm not going to that part. Yeah, so y minus n mu upon sigma under root n. So y in this case is x1 square plus up to x100 square minus n mu upon sigma under root n. So this n mu is same as expectation of these x1 square plus x2 square up to x100 square, right?
Yes, ma'am.
So it's the same thing. So there it will be what, 100 by 2. What is mu?
Yeah, ma'am, but the problem I faced is like the graded question, it had 500 instead of 100, and
Okay.
like by mistake I tried to do it with gamma of 100 by 2 and like sorry 500 by 2 and whatever was the corresponding variance.
So there even mean and variance was coming out to be different, correct?
I'm sorry,
What was that? What was the question there? I think
ma'am. It was very similar to this, but instead of 100 samples, we had 500 IID samples.
and I think just it was normal 0 1, I think.
Yeah, I think yeah. So yeah,
Yeah, so we take this mu. This mu will be the mean of xi square. So each of these xi square is gamma 1 by 2, 1 by 4. So mean of this is alpha by beta. So 1 by 2, 1 by 4. So it will become 2.
ma'am. Just for the last clarification, can you go back to the YouTube video once?
Yeah.
Uh, so the first time you have written gamma half and 1 by 4th,
Huh?
will that is the distribution for xi in general.
Xi square. Yeah.
Yeah, xi square in general.
Huh.
And like for x1 to x100, that is 100 by 2.
100 by 2. Yeah.
And for calculation of mu, we are to use the first one.
For the calculation of mu, you had to use you mean xi square, right?
Yes, ma'am.
Uh, yeah. Wait, look the video.
See, the n IID sample, the summation of n IID sample, in this case xi squares, sum up to gamma. Okay. And for CLT, we take this mu for each and every xi. So in this case, we need to calculate mu for each of xi square.
Yeah. So it's same, right? And n mu is same as like if you do n mu is the expectation of x1 square up to x100 square, and that will again come out to be 200. That will come out to be 200, correct?
500 by 2, 250. It will be.
Oh, you're talking about that one. Yeah. So that will be different. I don't remember exactly what is that. Is this clear or
Yes, ma'am. Yes, ma'am. It's clear. Thank you.
this is clear, right? Yeah. So
Ma'am,
yeah.
I have a question in week 8. Can I ask you that, ma'am?
Yeah. Okay.
Practice assignment week 8, question number 4, ma'am.
Okay. Yeah. Yeah. So what was the question? That was S to be sum over something. Start.
It was S square.
Variance thing, right?
Yes, ma'am.
Wait. Yeah, I will explain that. So you have x1 up to xn IIDX. Now x bar is given to be
Sigma
sum of
AI is
ai xi I varying from 1 to n, x expectation of x is mu, variance of x is sigma square.
Yes, ma'am.
Now you have to
Ma'am, even here I have one question, ma'am. Can I ask?
yeah.
Ma'am, here you have written x bar is equals to sigma ai xi, and the notation you used is capital Xi, and I believe this capital Xi will be equal to x1, x2, xn, ma'am.
Yeah, it's the same thing.
Yeah, but ma'am, in the question it is given small xi. So ma'am, will it not make difference any?
No. It's the same there. There it
Same.
means there's a sampling. It's okay.
Okay, ma'am. You can continue.
Yeah. So expectation of x is mu, variance of x is sigma square. S square in general is given to you as sum of ai xi minus x bar whole square. I is varying from 1 to n. So what do you have to, which part you want to know?
Actually, I expanded it, ma'am.
Okay,
Xi minus
so
x bar
let's
square.
find, yeah, let's expand this first.
Yes.
So you will get ai xi square plus ai x bar square minus 2 ai xi x bar.
Yes, ma'am.
This is summation. So this will become sum over ai xi square plus sum over ai x bar square minus 2 x bar sum over ai xi, right? Yeah.
Yes, ma'am.
Now, what you can write this as, you can leave this as it is. So this will become, so this part will become a1 x bar square plus up to an, sorry, x bar square again you can take it outside, and sum of ai, I assume it is given to be 1.
It is even 1.
1. So this will become
X bar square, ma'am.
x bar square, and this will remain the same.
Yes, ma'am.
Now come to this, so it will be 2x bar. This will be a1 x1 plus up to an xn, and this
Yes.
is given to as x bar. It is given in the question. See this one?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
So this is given to x bar, so it will become 2x bar square. So if you solve these two, you will get
Minus x bar square.
it will be ai xi square minus
Minus x bar square, ma'am.
yeah, minus x bar square. Yeah. So this is s square. Now we want to find the expectation of this term.
Yes.
So expectation of s square will be expectation of sum over ai xi square minus x bar square. So that will be expectation of sum over ai xi square minus expectation of x bar square, and x bar is a constant. Sorry, x bar square will be a constant. So no.
No, ma'am.
Okay. No. Yeah, it is a random variable. Sorry.
Yes.
So expectation. So you can take the expectation inside. So it will become expectation of ai xi square, yes, minus expectation of x bar square. So what is x bar?
Ma'am, it will come out to be sigma square minus sigma square by n minus mu square.
Sigma square by
n minus mu square, ma'am.
Minus
Plus mu square, ma'am. Plus mu square.
Plus mu square. Okay, let me just check. So x bar square. Yeah. So you're interested in expectation of this. So this is nothing but variance of x bar plus variance of sorry,
Plus
expectation
expected
of
value of x bar, ma'am.
value of x bars
Square, ma'am.
Yeah.
Yes.
So sigma square by n, and
Plus mu square.
expectation of x bar square is mu square. Okay. Yeah. Right. So this is right. So I can write this here. This is sigma square by n plus mu square. So this is minus mu square.
Yes, ma'am.
Now this part. So it will be sum over ai expectation of xi square.
Yes, ma'am.
So expectation of xi square is what? This will be
Ma'am, sigma square by mu.
variance of xi plus expectation of xi whole square.
Yes, ma'am.
So variance of xi is what is given?
Sigma
Sigma
square.
square.
Yes, ma'am.
Sigma square. This is mu square.
Yes, ma'am.
So this is a constant. So we can. Yeah. So this will become
Ma'am, this will become sigma square plus mu square, huh?
sigma. Yeah, because summation of a is
Yes,
1.
ma'am. 1.
This minus sigma square by n minus mu square
Mu
cancel out.
square will cancel out, ma'am. Yes, ma'am.
So you will be left with sigma square minus sigma square by n.
Yes, ma'am.
Yeah.
Ma'am, but this is not in the option, ma'am.
Wait, what is x bar?
Ma'am, this is what I was getting, but it was not given in the options.
Expectation of x bar. Oh, so here your expectation of x bar is what?
Ma'am, it will come out to be mu square.
Expectation of x
Mu,
bar.
mu, ma'am.
It will come out to be mu, and variance of x bar will come out to be what?
Sigma square by n, ma'am.
Sigma square by n.
No.
No, a1 x1 plus up to
Ma'am, it will come out to be sigma square.
ai square variance of x. It will not come out to be that. So this is our x bar. So you want to find the variance of this. So variance of this is a1 square variance of x1 plus up to n square variance of xn. So this will be sigma square sum over ai square.
Yes.
AI square, it is not given at to be 1. So the variance of x square is actually this.
Okay. Okay.
So there is the wrong substitution.
So, ma'am, we messed up because we are considering x bar is x1 plus x2 plus xn by n. But actually, it is not
it is
that.
given as x bar is sum over xi.
Okay. And we were taking that x1 to xn by n. That's why we missed it.
Yeah. So now you try to do it. Will be okay.
Yeah. So by putting this, you'll be getting
This
that.
is a general form. Yeah. Yeah.
Okay.
You should get the answer.
Yeah. Okay, ma'am. Thank you, ma'am.
Yeah. Okay. Go back.
And ma'am, one more doubt, ma'am.
Uh,
Ma'am, tutorial 1, question number 11, ma'am. Ma'am,
week 8.
yes, ma'am. Ma'am, I asked this question on discourse, ma'am, and you replied there and gave a detailed solution that, ma'am. But how you derived is a bit tricky, ma'am. So, ma'am,
Tutorial 1.
is there any questions similar to that in the end terms or quizzes?
What question now you're talking about? Which question?
Ma'am, it was given exponential, and we have to find the estimator for lambda, and it was minimum exponential.
Okay, why it was n lambda?
Yes, ma'am. I got it. It was n lambda, but I want to ask you that it was very tricky to solve that minimum because in its previous part it was directly coming out to be unbiased and directly lambda. But to guess that minimum of x1 to xn will be a distribution n lambda is very tough.
That is why we had given it as a hint. Use this to solve the question.
So, ma'am, such things would be given in the question, or we have to derive it?
We'll give such type of information.
So it would be given. Okay. Yeah. Thank you, ma'am.
But the derivation was not difficult, right? It was like
no, ma'am. It was easy, but ma'am, it was hard to think that it can go in that manner.
Yeah.
Derivation was very simple. Like it was from week 3, some 3.11.
Week 3. Yeah, it is from week 3.
It was easy, but ma'am, it was tricky to think in that direction.
Yeah, that is why we had given the information there in the question.
Yes, ma'am. Thank you, sir.
Yeah. Okay, so I'll go back to the confidence interval. So still there. No? So yeah. So let's say you have a parameter theta and you want to estimate this parameter theta. So what it will be like, you want to say that with some percent of confidence, this parameter, whatever is your estimator, that should be in some neighborhood of theta, right? So if let's say this is a normal distribution. Say this is a mu and this is a theta, and if we are saying with 95% confidence, it means this area should be 0.95, and these remaining area should contribute to the another 5%, that will be 0.05, right? Yeah, so these two will combine, give the area of 0.05. Now what I'm interested in, we want to find the confidence interval, that interval where we can say with this much confidence that your estimator mm, theta hat will lie in this interval. So who had asked this question? I just wanted to ask something. Who asked this question? Samit, you asked.
I asked in general to discuss the confidence interval, not any specific question.
Okay, yeah, okay. Yeah, so we want to find the confidence intervals. So using the Chebyshev's inequality, we know that probability of the estimator, let's say in general we call the estimator as theta hat or mu hat, anything, minus expectation of theta. So let's say it is theta itself, and this is your alpha is it should be B. It means this shows this reason. If you look at this shows this reason. It means with 95% confidence, your theta hat will lie in this interval. Now, how do you find the alpha and beta there? How do
How
you?
are we taking equality?
Sorry.
This is Chebyshev's inequality.
Yeah, Chebyshev's inequality.
So how we are equating the probability to beta? That is
That is given. This, what is this beta you want with if we are saying with 90% confidence or with 95% confidence, my my estimator should lie in this. So this shaded area, right? This is your beta. I mean, this 95% confidence. So this area will be 0.95.
no, but the inequality says it will be less than equal to, no?
Yeah, this beta is 0.95. See, if we say 95% confidence, what does it mean? So 95% confidence means with the 0.95 probability, your theta hat should lie in this interval. So that will be given to you in the question, like how much confidence you want. It can be 90%, 90%, 95%, depends on how much confidence you want, or 99%, anything.
No, but the Chebyshev's inequality says the probability will be less than equal to a particular value, which is sigma square by and delta square.
Yeah, so yeah, that gives the lower bound, right? Now what I'm saying, this probability is exactly this. If I write this, what does it mean? This is what you have a theta, and you want your theta hat to be this theta plus alpha, theta minus alpha. So if I write this, it means in this interval, in this region, your theta hat should lie. And this, if this is beta, it means they should give the probability 0.95. So let's write the Chebyshev's inequality. This is probability, let's say theta hat minus theta greater than alpha. So it should be less than equal to sigma square by n delta square. So in this case alpha square. So what does it give? It gives you the lower, upper bound, right? This gives you the upper bound for the probability. But this is the probability, correct? This beta is the
This,
probability. This sigma square
this
by
will be,
n. This
shouldn't
sigma.
it be 1 minus p, or because within bracket it is less than?
Which one? Within bracket?
Yes, ma'am. It should, ma'am. You are writing less than alpha, na, ma'am. So it should be 1 minus sigma
Okay,
square
okay,
by
okay.
n.
Yeah, sorry. Yeah.
Either it should be greater than
Yeah,
or
sorry for that. Yeah. So it should be 1 minus sigma square by n alpha square. Yeah. So it is nothing but the probability. This the bound that you are getting is on the probability, and we are saying this probability will be greater than this number, at least this. But what I am giving here is we are giving you the probability. This probability, you assume you want the probability to be 0.95 with 95% confidence. You want your theta hat to be in this interval. So it
So,
just
we are instead of inequality, we are saying that this probability is given.
yeah, this probability is given. So whenever you see 95% confidence, 90% confidence, 99%, whatever confidence you want, this is your B. Because if this is nothing but a probability, right? This is giving a bound on the probability.
Yes.
Your probability should be greater than equal to this term.
So this bound
Your
should be
probability
95% or more. That is what we are saying.
95, yeah, if you are saying this is 95%, so in this case it will be greater than, like, 95% is the lower bound, so it should be greater than equal to this. But here what I'm saying is this is exactly 95. You want with 95% confidence your theta hat to lie in this interval, theta hat, this interval.
Yes. So whatever inequality is there, so minimum 95% confidence and will be found out.
Yeah.
Okay. Whatever and we find, the minimum probability for, will be given as 95%, or if we vary the n, it will be more
It
than
depends on
95%.
in the question. Like sometimes you will see 90% confidence, 99% confidence. Accordingly, it will vary. So this is like if I'm saying beta, this is the reason. This is the reason. The shaded reason is beta, and the remain. So this area is covered by, if I'm saying 95% confidence, this area is 0.95. So the remaining this reason and this reason will contribute to 0.05 area, 0.05 probability. Now, whenever we have to find,
That means
yeah,
when from this formula, means from this discussion, I can conclude this probability of theta hat minus theta mod of less than alpha, the probability is greater than 1 minus sigma square by n delta n alpha square, right?
yeah, using cell shapes, yes,
So this 1 minus sigma square by n alpha square is giving the
yeah,
lower
0.95,
bound of this probability.
yeah, yeah,
If now from this equation, as n goes to large and large, so the sigma square by n alpha square become smaller and smaller,
and it will
and
become
the
1. Yeah, so if you look
probability
at the Chevy
becomes
shape, yeah,
1.
Chevy shapes inequality, if you look at, like, so what does it in general says is probability that theta hat minus theta less than alpha is greater than equal to 1 minus sigma square by n alpha square. So as limit n tending to infinity, your probability theta hat minus theta less than alpha, this will tend to 1. And if you look at the other form, so this is probability theta hat minus theta minus alpha, greater than alpha, less than equal to sigma square by n delta square. And this, if you take the limit, So it will tend to 0 as n tend to infinity. Your probability that your theta hat will lie outside this interval will converge to 0. So this is what in general it means.
So we are pushing the error towards 0.
We are pushing the error to, yeah, we want the error to be tend to 0. Yeah.
Ma'am, I have one more question from week 8. Ma'am. Can I
Uh,
ask you?
yeah, can I finish the
Yes,
confidence
ma'am. Yes, ma'am.
interval, then
Sure,
I'll go back? Yeah.
sure.
So that is what Chebyshev inequality. Now what I'm saying is you want just exactly 95% confidence. You want the probability to be 0.95, not less than that or more than that, exactly 0.95. Okay. So if I'm saying 95% confidence interval, so it means I want probability theta hat minus theta less than alpha is equal to 0.95.
Yes.
Now, yeah. So now your theta hat is what? So theta hat we have taken to be, let's say this was expectation and we have taken an estimator to be sample mean. So let's say this is our estimated x1 plus xn by n. Uh, and you know that this theta hat as increases, this will be okay. Let's take x1, x2, xn. These are, let's say, they are coming from IIT normal mu sigma square. Let's explain one of the cases here. So let's say all these xi's are coming from normal mu sigma square, where your mu is unknown, and sigma is known to you. Sigma is known to you. So if you want to estimate your parameter theta, because that is unknown to you, so one of the estimator we know as x1 plus x2 up to xn by n. So if you find the mean and variance, and if all these are IIT, we know that your estimator theta hat will also be normally distributed with mean mu and variance sigma square by n. This is what we have seen in week 7 last lecture.
Yes, ma'am.
Right? Yeah. So your mu hat will be n mu sigma square by n. So what we can write as z to be your normal, z you can write as mu hat minus of mu divided by sigma upon under root n. See, if you look at the CLT form, so what does it say? It says y minus n mu upon sigma under root n is normal 0, 1. So we have one more form that is, just expand this. So x1 plus xn minus n mu divided by sigma under root n. Let's multiply numerator and denominator by 1 by n. So you'll get x1 plus x2 plus xn by n minus mu upon sigma under root n divided by n. So this is nothing but x bar minus mu divided by sigma upon under root n. So this will also be normal 0, 1. So this is also normal 0, 1. So same thing. So what is this? This is a sample mean, and this is expectation of sample mean, and this is standard deviation of sample mean. Now let's come back here.
Ma'am, I have a question here. Can I ask you that?
Yeah,
In
yeah.
this, not this part, ma'am. Left side. Can you go to left?
Yeah.
Yes, ma'am. Ma'am, here you are taking theta to be x1 to xn by n. Then your standard deviation is coming out to be sigma by root n. If I
Sigma by
change
root
the
n.
yes, ma'am. If I change the estimator mu hat, then this standard deviation will also be changed, ma'am.
Yeah, in that case, that will be changed.
And then I can't do that sigma by root n directly. Then I have to calculate the standard deviation for mu hat, ma'am.
Yeah.
Okay, okay. Okay. And ma'am, this is only standard deviation. It is not the standard formula that I am directly taking sigma from the distribution of mu and directly dividing by root n how many samples I have. This is not this formula, ma'am. Or is it
Uh,
this?
which one?
Ma'am, you have
This one?
written z. No, ma'am, stay here,
Okay,
ma'am. Stay here.
here.
Ma'am, you have written z equals to mu hat minus
You
mu
had minus mu
upon sigma
sigma
by
under
root n.
root n. Yeah.
Yes, ma'am. Ma'am, here what I conclude is that the denominator part, that is sigma by root n, is the standard deviation of mu hat,
You
ma'am.
had. Yeah.
If I change the mu hat, ma'am, and
Yeah.
then what I am doing, ma'am, there are two conclusions. One we can draw is that the denominator is a standard deviation of mu hat, and the
Uh,
other part could be that the denominator is just the standard deviation of mu divided by the number of sample under root of number of samples. So ma'am, which
uh,
estimation is
sorry,
correct?
sorry. Second part, what did you say?
And second one is the denominator part is the
Huh?
standard deviation of mu whole
This
upon under root number of samples.
this one.
No, ma'am, left side, ma'am, left side, z, ma'am, z.
So other is what in the denominator you want sigma under root n.
No, ma'am, I am this part only sigma by root n. But ma'am, it could be concluded in a way that this denominator is nothing but just standard deviation of mu
You had
divided by the number of samples in sigma hat.
standard deviation of mu. Mu is expectation. No? How will you find
No, standard deviation of our ma'am. What
estimator?
estimator.
Yeah, that is correct.
That is correct, ma'am.
Sigma is what? Sigma is standard deviation of your x.
Yes, ma'am.
Standard deviation of x. Sigma upon under root n is standard deviation of sample mean.
Yes, ma'am. Ma'am, I got it, ma'am. That denominator is the standard deviation of x bar, ma'am. That is our
Sample, yeah,
estimate.
sample mean, yeah.
Sample mean, ma'am. So can we conclude that, ma'am, if it change our mu hat, the standard deviation will also change, ma'am. Let's say we instead of dividing by 10 n, we are dividing it by 2n, ma'am. So, ma'am, the standard deviation will also be changed, ma'am.
Yeah, then in that case, that will not be a sample mean.
Yes, ma'am. But the standard deviation for x will remain same, ma'am.
Standard deviation will remain the same.
For x, it will remain same, ma'am.
Yeah, standard deviation will remain the same
Yes,
for
ma'am.
x. Yeah.
Yes, ma'am. So, ma'am, what I am concluding is that, ma'am, in denominator, instead of standard deviation of x bar, we can also write it as standard deviation of x divided by number of elements in our estimator. In this, we have n samples. In that, if we divide it by 2, it will become 2n samples. So, can we write sigma by root 2n?
Yeah, sigma by root 2n you can write, but your sample should be x2n, like x1 to x2n.
It will be till x2n.
Yeah, then you can write it. Yeah.
So, ma'am, can we do it the way I am doing, like by taking x, not the standard deviation of x bar? I am assuming it to be x and then concluding that sigma standard deviation of x divided by number of samples ka root.
What did you say?
I said, ma'am, this sigma by root n is standard deviation for x bar, ma'am.
Yeah.
Okay. And then this sigma by root n can also be derived by standard deviation of x, that is sigma whole upon number of samples n.
Yeah, it's the same thing. Yeah.
By root n.
Yeah.
So is this thing will be valid for every mu hat? Or
This
for
is
this?
for sample mean. So
this is only for sample mean, or this will be valid for every?
What is this? According to your central limit theorem, you're like your sample mean will be like approximately distributed. Like the mean will be mean of x, and the standard deviation will be sigma upon under root n. And if you divide that, that becomes normal 0, 1 in general.
Lakshmi,
Yeah.
if you have any specific problem means any example, then with respect to that, if you discuss, then everybody get benefited.
Actually, I don't have. By this time, when ma'am was discussing this thing, then only I got this point that could we write it like this or not.
Okay. Okay.
I don't have any example for it.
Ah,
Whatever questions is given in the tutorials or whatever, ma'am. What I did there was that I was finding standard deviation for mu hat,
hmm.
but here I got that what we do in that CLT, ma'am. We
Sam,
find sigma
yeah,
for
like your X
x.
bar, mean of X bar, yeah.
Yeah, mean of x bar. What we do in CLT is that, ma'am, we find, ma'am, the standard deviation which we are taking, that is for x, not for x bar, ma'am. And then we are dividing, multiplying it by root n, that is number of samples, ma'am.
Number of samples.
Yes, ma'am. So, ma'am, can we do that same thing here? That
It's the same thing, no?
is the
Actually,
same
if
thing.
you
So we can do
if
that.
you come this way or that way, it will same, na. It is the distribution whose has a x bar and it's minus its mean by standard deviation.
So both of
If
these
you
things are derived from the same thing, ma'am, basically.
Yeah,
if you
see, if even this y, like the mean of y is nu, and variance standard deviation of y will become sigma upon root n. Yes,
Okay. Both the things. Okay, I'm getting it now.
that is what I had proved here.
Yeah. Okay. So, ma'am, do you want to carry this forward, or I have other question on
Uh,
that?
yeah. So, Samit, do you want me to explain more confidence interval?
now basic idea of confidence interval I got it.
Yeah, so
Miss
whenever you have to find, like, if you have some problem, then what we do, we need to find alpha, right? Like if beta is given, then you
Mhm.
need to find the alpha. So how, okay, let's proceed with that. So probability mod of theta hat minus theta less than, but theta is our sample mean. So this less than alpha is equal to, let's say this is 95% confidence. So if what you can write it as,
1 minus that thing,
uh,
sigma square by.
we'll write it in the form of standard normal. So it will become mod of theta hat minus theta upon sigma upon under root n will be less than equal to alpha upon sigma under root n, that is 0.95. So if you plot the graph, this is the graph. So yeah, this point is alpha upon so this is divide sigma upon under root n, and this is minus alpha upon sigma upon under root n. So this is your beta, which in this case is 0.95. So this value, this z value, this will be given to you in the problem will provide you. So this alpha by upon sigma upon under root n is some z value that will be given to you in the question. Uh, okay, I don't know how to. Do you know how to see the normal distribution table? So this value, right? This value, how do you find this value? So if this is point, this area is 0.95. These two remaining should be 0.005. Sorry, 0.05. Now you have to split in both the sides. So you'll have to divide 0.05 by 2. 0.05 by 2. So you will get 0.025. So individual this area it 0.025. Now, if you subtract 1 minus 0.025, what you will get? 1 minus 0.025, you will get 0.97.
0.975.
Yeah, 0.975. So now you'll have to, if you look at the normal distribution table, standard normal distribution table, for what value? I think for 1.96, it will come out to be this probability. So we'll substitute alpha by sigma upon under root n to be 1.96. So your alpha you can calculate from here. So it will be 1.96 into sigma upon under root n. Your sigma is known, your n is known, so you'll find alpha. And if you have to find the confidence interval, it is again x. It will become your theta
Mu
hat
minus sigma
x bar. Yeah.
plus mu
X
plus
bar
sigma.
plus alpha. This will be a
Correct.
confidence interval.
Okay.
Yeah. Yeah. Who has a doubt? Yeah, you can
Yes,
ask.
ma'am. Yes, ma'am. I have it. Ma'am, one more thing I want to add on, ma'am. In tutorial 3, ma'am, these values are not given, ma'am.
Oh, okay.
We have to check it or on from the normal table, ma'am. It is not given. Otherwise, it is given in the upper portion, starting in the.
Okay,
It is
okay,
often given, but in tutorial 3, it is not given, ma'am.
okay.
And,
We'll try to upload that. Just write it here.
ma'am, my doubt is assignment 8.9, question number 2, ma'am.
Assignment 8.9.
Yes, ma'am.
Properties of estimator. Question number?
Second, ma'am.
Okay, second. So you have x1 to xn. The IID sample from uniform 0 theta and estimator for theta is given by theta to be 2x bar. Yeah. So you have to find mean square error for theta hat.
That is same as risk now, ma'am.
Yeah, that is same as risk.
Yes, ma'am.
That
So,
is
ma'am,
the doubt.
yes, ma'am. Ma'am, I am getting answer to be 7 theta square by 12. But the given answer is that
Yeah.
the given answer is theta square by 3n, ma'am. So, ma'am, we get theta square by 3n when the bias is 0. But in this case, ma'am, the bias is not 0. So, how it could be
Bias
theta
is
square?
not 0. Wait, I will just write it here. Can you tell me x1 to xn was uniform 0 theta?
Uniform 0 to theta, ma'am.
And your theta hat was given to be 2x1,
2x bar, ma'am. 2x
2,
bar.
2x bar.
Yes,
Okay, let's calculate bias of theta hat.
ma'am.
So
It
bias
will
of
be,
theta
ma'am,
hat
theta by
will
2.
be
It will come out to be theta by 2.
expectation of 2x bar so plus xn upon n. So 2 upon n and mu. So 2 mu. What is the expectation of
Theta by 2, ma'am.
theta by 2? Okay. So it is coming to be theta 0, right?
Ma'am, how it is coming to be 0, ma'am? It
What
is,
is theta by 2?
ma'am, it is expectation of, ma'am, this x.
Expectation of x, right? And here you have what 2, right? Here. So you'll
Yes,
have
ma'am.
to multiply by 2. So it will get cancelled out and it will be just theta.
Yes, ma'am. But from this, we will subtract theta by 2, na, ma'am, or we will subtract theta.
No, you subtract theta. So if we say if you have to find bias of theta hat, it will be expectation of theta hat minus theta. So expectation of theta hat is coming out to be theta and this is theta, so it will be 0.
Okay, okay. Actually, I was subtracting theta by 2 from it, ma'am.
Bias of theta hat minus, expectation of theta hat minus theta. This is bias.
So I just, if because I got expected value to be theta by 2, I exchanged theta also by theta by 2, ma'am. That was silly error, ma'am. Okay, okay.
Yeah.
Yeah, got it, ma'am. Got it. Then it will come out to be, ma'am, theta square by 3n, ma'am. Thank you.
Okay, yeah, thank you. Okay, so anybody has any doubt? Any more doubts? If you don't have any doubt, we can wind up the session now.
Thank you for the session.
Yeah, thank you. Yeah,
Thank you. Thank you.
yeah, thank you. Okay, we wind up the session now. Thank you all for joining. We'll close the session. Karthik, you can close the session.
Okay, okay, Nikita.
Yeah, okay. Yeah, thank you.